So let us start with this part, okay? The definitions of the resolutions. So what's mean resolution? Resolution, generally, we can define as the shortest distance between 2 points on a specimen that can still be distinguished as separate entities. Now, what does this mean? So if in my object, we have, this is the actual. Okay. So if you have very high resolution compared to low resolution, what will happen here is for high resolution, you still can see it as 2 points, but low resolution, you will see 2 points actually overlap together. So this one is a high resolution, this one is a low resolution or poor resolution. Are you clear? Because it cannot show me the actual. The actual actually got 2 dots. By using a higher resolutions, let's say for example, we use a higher resolution microscope, I will be able to see 2 points. But if you use a low resolution or poor resolutions, then only can see 1 point. And the limits of resolutions, okay, here is not because of my microscope, but because it's limited by the wavelength of the radiation. Are you clear? As long as you didn't change the wavelength, you won't be able to improve the resolution because the limit of resolution is about half of the wavelength of the radiation we use to view the specimen. If you look at light microscope, why we say light microscope have poor resolutions compared to electron microscope? Because we use the visible light. If you check the visible light, what is the wavelength? So visible light wavelength is roughly about 400 nanometer all the way to 700 nanometer. So 700 nanometer is the red light, and 400 would be violet light. Are you clear? Okay. So what will happen here is if our microscope if we use the violet light, normally we won't do this. Okay, we use the white light, right? If we use a violet light, so means that the wavelength of the light equal to 400, roughly 400 nanometer, then resolution of the light microscope will be half of it. So means about 200 nanometer if we use the violet light. But if you use the red light as the source of radiations in your light microscope, then the resolution will be 350 nanometer. So what is this value tell you? Okay, so let us look at this explanation in general, then you will be able to understand what is meant by resolution's value here. Okay. So now let us look at these resolutions. Okay, I give you 3 scenarios here. Okay, so if you have light source using the red light, which with the the wavelength equal to 700 nanometer. Okay, red light. Okay, and another ones we're going to use the violet lights or blue violets with the lambda equal to 400 nanometer. Okay, so first thing, let us look at resolution. What is the resolutions of the microscope using red light? So half. Okay, resolutions equal to half of the wavelength, roughly. Okay, so equal to 350 nanometer. Okay. Next, how about violet light? Half of the 400, so equal to 200 nanometer. So what is this resolution actually mean? Okay, so let me show you. If you look at this resolution, it's the shortest distance. Always remember, it's the shortest distance where my optical instruments can distinguish it as 2 points. Okay, so now what's this mean? Let's say first scenario, first case, first example. If first example, if my distance between two objects, if the distance between these two objects, let's say I put it as 300, okay, if the distance 500 nanometer, okay, the distance between these 2 points is 500 nanometer. Okay, so if you use a red light, as the source of radiation, the shortest distance I can differentiate it as 2 points is 350. And here is 500. So means that if you use the light microscope using the red light, I can see as 2 points. Are you clear? No issue for me to see at 3 points, because why? The shortest distance I can see it, okay, between the 2 points that I can still see as 2 points is 350 for red light microscope. Violet light, no problem, because the shortest distance is 200 nanometer. If 200 nanometer basically means that anything more than 200 nanometer, I can also see it as 2 points. Are you clear? Okay, this is the first state. Now let's look at the second scenario. Example 2. So now my object, the distance, actual distance now, let's say 300 nanometer now. Okay, if you use the red light microscope with the resolution of 350, means that maximum, okay, the shortest distance I can have 350, I can differentiate it. Anything less than 350, I will see it as 1 point. So means that if you use the light microscope by using the red light, then you can see these 2 points overlap together. You can't differentiate them, even though you increase the magnification. Regardless of how high the magnification, you won't be able to see as 2 points, because why? 300 nanometer is lower than 350. My ability only up to 350. Anything less than 350, I will only see as 1 point. So means that for red light microscope, poorer resolution. Why? If you compare to the violet light is 200. So means shortest distance, minimum, the shortest I can have 200. Anything more than 200, I will be able to see it as 2 points. Can you see that? I can see a 2 point. So this one, better resolution. Okay, can? Now, third scenario. Okay, so if the 2 point, the distance here is 100 nanometer. It's 100 nanometer, then you can see that 100 nanometer shorter compared to 350 and 200. So therefore, both microscope will show me overlap of 2. Are you clear? Overlap of 2. So based on these diagrams, then we do know that if you compare, then I can say that violet light microscope have better resolution compared to this poorer. Why? Because of the wavelength used in this microscope. So generally, okay, you can see that when your value of resolution is low, then better resolution. Are you clear? It's something like this, right? If you can run with a short period of time, shortest marathon, means Olympics, 100 meter, you run 9 seconds. Good, right? It's not counted like, oh, you run 20 seconds, then you're better, right? The shortest the times, the better. Same goes to the resolutions. The lower the value of the resolution, the better the resolution is. Okay, are you clear about the resolution, the context of resolution? Okay, understand? So once again, I say that, okay, look at the value here. The value of the resolution lower means better resolution. Okay, so you can take a photo if you need for this summary, example. Always remember, the lower the value of the resolutions, the better or the higher the resolution it can be. Are you clear? It's similar to our Olympics. Okay, the faster you can complete, the better, right? So the shortest the time taken. Same concept like this. Okay. So that's why I said that the maximum resolution of the light microscope, not light, sorry, light microscope, my mistake, is correct, the notes. Okay, so that maximum resolutions of the light microscope is about 200. It's not equal, but it's about roughly, okay, 200 nanometer. So because why? The shortest wavelength that we can use of the visible light is 400 nanometer, which is the violet light. So therefore, with this resolution, maximum I can get is 1,500 times. And actually 1,500 times, we never use it in our lab. Our lab, we're gonna use in our lab. So we do have this, okay, in our lab right now. Our magnification power of the light microscope that we normally use, either 40 times. Okay, 100 times and 400 times max. Are you clear? So how you get 40 times? How you get 40 times? 40 times basically is 10 times eyepiece and 4 times objective lens. Okay, eyepiece, objective lens. Okay, so for you multiply 2 times, right? It's a compound microscope. So you compound it. So it means that 10 times eyepiece, 4 times objective lens, total 4 times 10, 40 times. Okay, 100 times basically your eyepiece, you don't change it, but objective lens, you can up it to 10 times. So you get 100 times, and you can continue to use 10 times for eyepiece and 40 times for my objective lens. 400 times, this is the max that we use in our lab. 1,500 is too high. Are you clear? And actually, you won't see much detail. Okay, so just generally, we use up to 400 times. And you realize that what is the difference between the times putting at the back and the times put it in front? When you put times at the back is the power of your lens. So this lens can magnify 10 times, 40 times. That is the power of the lens. But when you draw it, okay, a specimen, oh, the magnification, okay, equal to times 200. So the times must be in front when you calculate it. This one is not calculated. This one is already stated on the lens. Are you clear? How many times is the magnifying, what we call this, power of your microscope? Even sometimes you can see that some books also use it wrongly. Okay, times putting at the front, actually not correct. Okay, times at the back indicate what? Indicate is the power of the lens that we use. Times in front indicate what? Calculated magnification based on your drawing. Okay, so now, what is the maximum magnification of the microscope? The power of magnification is 1,500. If you continue to use a very powerful magnification, it won't increase the resolution because the problem is not on the lens. So let's say, for example, I can always photocopy, okay, make it larger, right? If photocopy, you can make it larger. So you can continue to make your picture larger, but no extra detail you can see. It won't improve the resolution because the limitation here is the light, the what we call this, the visible light that we use. Okay, so now, if you look at this diagram, the electromagnetic spectrum, you can see that our visible light is somewhere here. Okay, so from roughly about 400 to 700, where 700 is the red light, 400 is the violet light. So this is a spectrum. Okay, so the question here is, if you are an engineer for this optical engineer, okay, your company asks you to design a microscope so that you can improve the resolution, okay, which make your microscope better than the current light microscope. Which radiation you are going to use? Always remember, the shorter the wavelength, the better the resolution. This is the concept right now. Wavelength shorter, okay, better resolution. So it means that your choice of the radiation, your choice of the radiation must be lower than 400 nanometer. Then you can increase the, you can increase the resolution. You cannot continue to use this. Are you clear? You cannot continue to use this wavelength because why? You cannot improve it anymore. You want to improve the resolutions, definitely I have to use the lower wavelength. Are you clear? Okay, so what we can use? Ultraviolet, X-ray. Are you clear? Ultraviolet or X-ray. So the question here, can I use gamma ray, cosmic ray? Answer is yes, but they are very, very radioactive. Are you clear? So we don't use gamma ray and cosmic ray. You try to imagine that every day you want to view the cells, you expose yourself to gamma ray and cosmic ray. Even X-ray and UV also, they can cause the mutation to take place. That is, but at least they are not so dangerous. They are dangerous, but they are not so dangerous compared to gamma ray and cosmic. So we don't choose cosmic ray, we don't choose gamma ray. In fact, scientists developed the microscope using the X-ray and also the UV. Okay, so why we choose UV and X-ray? Because they have the shorter wavelength compared to the visible light. Can you see that? Shorter wavelength. So when you have a shorter wavelength, means that your microscope will have better resolution. Okay, but what is the limitation of the chosen radiation? If you choose X-ray and UV, we do have one problem. Recall back to what we learned in our microscope, the light microscope. We do have a condenser, right? What's the condenser? Condenser is a lens that helps us to focus the light onto my specimen. Okay, so generally you can see that here. Oh, sorry. This is my specimen. So you have the condenser. So condenser, what is the function of condenser? So your light source like this, so you can actually make them focus on your specimen. Can I not? Can I see that? The light, how the light pass through. Okay, you can focus them. Okay, when the lights go into the lens. Can I not? Because we want to focus so that we get a clearer image. Now the problem here is UV and also the X-ray cannot be focused by using the lens. Are you clear? We won't be able to focus them using the lens, so making them a not so suitable. Okay, they meet one criteria, shorter wavelength, but we can't focus them. UV can't focus them. How you focus them? They are not the visible light. X-ray, you can't focus them. Are you clear? So therefore, make them not so suitable. Okay, so the answer here is you can choose X-ray or UV because they have shorter wavelength compared to the visible light wavelength. But the problem is we have a difficulty to focus the X-ray and the UV to produce a sharp and clear image. Okay. Now, so we go into depth N again. If we can't use UV, we can't use X-ray, how we can improve? Okay, until scientists discover that we can use the electron beam. Now, be careful, not electrons, but electron beam. So how we can generate the electron beam? We use the electron gun. Okay, so means that if you understand the concept of atom is surrounded by the electron. Okay, so if we provide sufficient energy, we can actually eject this electron out from the valence, from this the outermost shells. So it means that these electrons, okay, will be free electron. So this electron, because we gain high energy, so this electron actually will move, okay, towards the directions that you want them. Because something like gun, like you shoot the full bullets, you will go to the direction that you want them to go. So these electrons will behave, when they move, they will behave like the electromagnets with wavelength now. Electron itself cannot have wavelength. If you look at electrons here, they can't have wavelength. But this electron beam, they will have the wavelength. Okay, so this one we call as electron beam. They are accelerated electrons, so they can move. When they move, they behave like electromagnetic radiations, and you look at this, we can actually, based on the energy, the highest the energy, the wavelength will be shorter. So as low as 1 nanometer or even lower. Are you clear? Can you see that? Compared to the visible light, 400 nanometer. Now this one, 1 nanometer only. So making it the resolution of electron microscope around 0.5 nanometer. Can you see that? Are you clear? Okay. So basically highlights the words electron beam, not electrons. Electron beam or accelerated electrons is a very suitable form of radiation for the microscope now. Why? First, they behave like electromagnetic radiation. Okay, with the effective wavelength as low as about 1 nanometer or even lower. Okay, so it can be used to resolve very small subcellular ultrastructure. For example, if you use the light microscope to see the membrane, you will only see one line. But if you use electrons microscope, then you can see two lines because of the phospholipid bilayer. Why? Why we can't see it? Because the thickness of the membrane is 7 nanometer. If 7 nanometer, if you use the light microscope, I only can see. Maybe use a light microscope only can differentiate anything more than 200 nanometer if you use a violet light. But if you use electron microscope with the resolution about 0.5 nanometer or 1 nanometer, then you will be able to actually resolve the membrane. You can see as two lines, where the first line represents the hydrophilic head and the pale region at the center represents the hydrophobic tail of our phospholipid bilayer. And because electrons, they are negatively charged, so we can use the electromagnets, okay, to actually focus them. So one of the example how we can do this, if this is electron beam, we can put the electromagnet with the negative end here. So negative, they repel. Then when this electron pass through this electromagnet, you will be able to actually bend them and focus them onto our specimen. Are you clear? So this is how we can use the electron beam as our source of radiation. So what is the benefit or what are the advantages using electrons beam? First, they behave like electromagnetic radiation with the wavelength less than 1 nanometer. So means that the resolution is roughly about 0.5 nanometer. And the best thing here is we can focus them by using electromagnet. Okay, so with this, I stopped my recording.